This is a quick overview of the periodic table, the way we organize the elements of matter that we deal with in chemistry. Look at the structure of the periodic table. Notice that it's choppy, it goes up and down. I like to say it looks like a city skyline with a building on the left, maybe an office block on the right. Okay, it isn't a smooth structure. Why is that? It's because the periodic table is made of blocks. Here are a bunch of blocks stuck together, somewhat resembling the structure of the periodic table. What I mean by this are the electron orbitals. The electron orbitals are divided into 4 blocks: the s block, the p block, the d block, and the f block. Sally's poor dog flatulated is the mnemonic device. All of them are in the right location with one exception. Notice helium is the one exception to this. This is just the order that the electron orbitals fill. If you follow the periodic table, read it like a page of a book, go from the first period to the second period to the third period line by line, you will basically see the sequence in which the electron orbitals fill, which gives rise to what we call periodicity, which is the repeating pattern of elements' properties. I always prefer to show the periodic table this way, in its correct form, in its complete form. However, to save space, many prefer to chop out the F block and drop it down to the bottom. This is because the F block is made of mostly elements that are fairly rare, and many are radioactive and synthetic, so it's almost like they don't matter so much. I think this defeats the purpose of understanding the structure of the periodic table, and it often leads to confusion. So whenever possible, I will avoid this, but let's call this the chopped periodic table. I will stick with the intact one. So when we look at the periodic table, it is really divided into 3 main groupings. The groupings are determined, strangely, by the size of the atoms. It might not seem important, but there's a trend for the size of atoms that basically drops as you go across to the right, and then it spikes again in the next period, and then it drops as you go to the right, and then it spikes again in the next period, and so on. This pattern gives rise to what we call metals and nonmetals. Because essentially, if you have a big atom, like the ones on the left and at the bottom, well, you're not going to have very much control of your valence electrons because they are going to be far flung from the nucleus, far out away from the nuclear attraction that's supposed to keep them in place. On the other hand, if you are on the right side of the periodic table or near the top of the periodic table, you are much more likely to have smaller atoms where the valence electrons, the ones on the outside, are not very far from the nucleus, and they are able to be held very strongly by the nuclear attraction. This is what gives rise to metals and nonmetals. This is the primary reason. It's easier to see if I shrink the periodic table even further into what we just called the S and P block periodic table. This one, you can really see the trend, how all of the atoms on the left are bigger, and then they pretty much shrink as you move across to the right. The ones on the right would be the nonmetals because they're small. The ones on the left would be the metals, except for hydrogen, because they are large, and at the bottom, metals, because they're large. Metals occupy a huge amount of the periodic table. The vast majority of elements are metals. A very, very select few elements are right on the boundary and they are called metalloids or semiconductors. They're not easily classifiable as metals or nonmetals. Some of their properties depend on temperature. You could think of them as having about half the properties that metals have. And finally, we have the nonmetals, which have essentially none of the properties that metals have, or maybe just a few like carbon, maybe just a couple of the properties metals have. Nonmetals are defined by what they are not. It's kind of a shame they have this name. They should probably have a better name because these are many of the most important elements on the periodic table, and we're defining them by what they're not. So the periodic table, when you look at it this way, well, we could talk about percentages. I wonder what percent are metals. 78% of the periodic table is made of metals. What I mean by this is of the 118 elements that we have right now, 92 of them are metals. So 92 divided by 118 times 100 rounds to 78%. Nonmetals, on the other hand, only seem to make up 17% of the elements on the periodic table. Now that's interesting. That's a very small percentage. You would not want to have that as your test score. Metalloids are even worse, 5% of the periodic table. And yet, the nonmetals dominate the universe. Why is that? That is because of abundance. The word abundance basically means how commonly something is found. If something is abundant, it's found very, very often, very frequently, all over the place. If something is incredibly abundant, it becomes ubiquitous. You just find it everywhere you look, all over the place. So water is ubiquitous on the surface of the earth. Abundance is the reason that we live in a non-metal universe. If you look at abundance of elements in the universe, these are ranked in order by abundance. Hydrogen is overwhelmingly the first element. Not just atomic number one, but number one, most abundant element. In fact, there's more hydrogen than all the other elements added together times 10. That's how much hydrogen there is. Then helium comes afterwards, oxygen, neon, nitrogen, and carbon. Those first 6 elements, the 6 most abundant elements in the whole universe, are all nonmetals. So because of that, we live in essentially a nonmetal universe, peppered with metals. After carbon comes a metalloid, silicon, and finally we get to a metal, if you look way over to the right, magnesium, which is the most abundant metal, followed by iron. Those elements are very abundant, and if you want to know why, well then you have to learn about fusion in stars. If we look at our sun itself, the distribution of elements in our sun is similar. Some of them are shifted around, like neon is in a different position, but still, obviously, the sun itself, the vast majority of it is made of nonmetals. The first 5 elements in the sun are nonmetals. Even in the Earth, which is a kind of a rocky planet, so you'd expect there to be more metals involved, and of course there are. Still, for the Earth itself, oxygen is the dominant element, more than any other element, which makes it a majority non-metal planet. Silicon is second because you need silicon and silicates, which makes up a lot of the Earth, a lot of the mantle and crust of the Earth. So that's number 2. Well, that's a metalloid. And then aluminum. Well, there's a lot of aluminum on this planet. It's the 3rd most common element on this planet. Then hydrogen. Okay, so it's not quite as obvious with the Earth, but still, nonmetals dominate, at least more than metals do. In our body, in any living thing, the composition, the abundance of elements in a living thing, like ourselves, is much more similar to the composition of the universe than it is to the composition of the Earth. We are made largely of hydrogen and oxygen. Of course, we are carbon-based life forms. You couldn't really have any of the molecules of life without carbon. And then nitrogen. The first four are all non-metals. And then, of course, we have calcium. Well, you got to hold us up with some bones. So you need a lot of calcium for the structure of our bones, and so on. But still, we are mostly non-metal. So think about this. You are a non-metal entity living on a non-metal planet, going around a non-metal star in a non-metal universe, even though 78% of the elements on the periodic table are actually metals. So when we look at the periodic table, you can chop it many, many ways. Some groups I'm going to skip over, so I'm going to do a very sort of trimmed down version of the families of the periodic table and the groups of the periodic table. I'm just going to emphasize certain important groups. So the first group on the periodic table is the alkali metals. They're called this because they often make alkali or base compounds after their reactions. These are metals, but they don't match your stereotype for metals, like really, really hard materials. You can squish them between your fingers, just like you can clay or maybe gum. They're kind of unusual looking. Plus, they're so reactive that it's hard to keep them pure. We have to store them under oil to prevent them from reacting with the moisture in the air. And when you do drop them into some water, like liquid water or even ice, they will react very violently. They will sometimes burst into flames, sometimes explode. Very dramatic reactions. The next group is the alkaline earth metals. Well, these are pretty reactive too. They're just not as reactive as the alkali metals, so they're often overshadowed by their more reactive neighbors. Okay, the most abundant element in the universe, magnesium, is one of these. So we have a lot of these elements in a lot of common chemical compounds. Then we have the rare earth metals. Well, this is essentially the F block. The F block is also called the lanthanide series and the actinide series. These are the ones that cause confusion on the periodic table because they chop them out, drop them down to the bottom. I guess people don't think they're very important. A lot of the ones, especially in the actinide series, well, they're all synthetic, they're all radioactive. The most famous member of the rare earth metals is probably uranium. And then there's also neodymium, which is included in a lot of powerful magnets. The transition metals include metals that are transitioning between the S block and the P block, and they include things like iron and copper. Okay, there are a lot of our very common and useful metals. These are your sort of stereotypical metals most of the time. Within the transition metals, there is a smaller group. This one is often omitted from chemistry instruction, but I think it's very important to understand this grouping, including copper, silver, gold, platinum, mercury. These elements are called the noble metals. These are the original nobles of the periodic table. Ancient alchemists, before chemistry was a science, noticed that they didn't react very much. They didn't react normally with acid, and so they considered them the noble metals, sort of living in castles, lords and ladies, kings and queens, right? And all the other metals, well, they're just the regular old metals. Those are the base metals. Base metals react with acid. Moving on, we've got the main group metals that include things like tin and lead. Tin used to be very, very frequently used in everyday life. Now it's often been replaced by other materials. Kind of sad. Okay, also aluminum is in this group. Aluminum is one of the metals that has replaced tin. Aluminum used to be more expensive than platinum until they found an easy way to isolate it from compounds. The halogens, or some people say the halogens, okay, is a very important group. Halogen means salt maker, maker of salt. And they do that. They make salts usually with the alkali metals. Fluorine, chlorine, bromine, iodine, astatine, tennessine. They all end in INE. Those are the only elements on the periodic table that end in INE. Very easy to identify if it's a halogen. And I like to call them the haloed halogens, or you could say the haloed halogens. It works either way because they're famous and they're important in chemistry. They're also a very, very reactive group of elements. Then we have the noble gases. Well, these are definitely the most noble elements on the periodic table because they are the least reactive. They don't associate with the riffraff other elements. They live their whole lives in their little castles. They don't need to work for a living because they've got it made. The nobles are the ones that all the other elements look towards. They admire them. They envy them. They want to be like them. A lot of chemistry can actually be understood by imagining other elements trying to become as much like noble gases as possible, because noble gases are the model of stability. They are the epitome of being a stable atom, especially neon. If you had to pick one, I would say neon is a perfect 10. And look at its atomic number, number 10. So looking at all these groups, you can understand some things about the periodic table from these. Obviously, there's more to go into. There's more to it than this, but you can get a fundamental understanding starting with these groups. When we say periodic table, well, we don't mean a table you would sit at, although there is a guy that made a periodic table that you could sit at where every box has a sample of the pure element inside it, supposedly, but I wouldn't sit too close to the radium end or the radon end. I would sit closer to the hydrogen or the helium end of the periodic table if it was a literal thing. Another thing to think about is, what about antimatter? Well, antimatter, so far we've only been able to make two elements in antimatter, anti-hydrogen and anti-helium. So I guess that's the anti-S block. I don't know. And of course, there remains to be discovered many, many things in science. There could be another block of the periodic table that would be unlocked after element 120. If we get to element 121, we'll probably be in a brand new block. Also, what about dark matter? We don't know. We're still trying to figure out what dark matter even is. So just keep in mind that science is expanding. We're always learning. There's lots of things to learn. So I don't want to present it as if we've got it all locked down and figured out. Okay, well, thank you for listening to my quick overview of the periodic table.